Hello again. This is video lecture 35.3, and we're going to talk about section 4 in chapter 35 and talk about a phenomenon known as interference from thin films, interference with light waves. And when we talk about thin films, we are talking about a thin region of material, transparent material, with some index of refraction, which is a layer, and so there are two other materials on either side of it. So the picture that we show here is kind of the standard way we imagine this situation. In some sense, we've got three layers here. We've got some material to the left of our film, and that material has index of refraction N1. We've got some material to the right of our film with index of refraction N3. And then the film itself is represented in the middle here. It's got some index of refraction N2 and some width or length, whichever word you wish to use, L. Now the picture here is implying a situation a little more specific, namely materials 1 and 3 on either side of the film are air. And we'll talk about it that way. But we're going to then also eventually ask you to think about the situation when one of those films or one of those materials on either side of the film is not air. All right. So we're going to send in light. And we'll represent that here in our drawing with this initial ray coming in on the left interface of the film. Now the picture shows the ray, the incident ray, coming in at an angle theta, right there, to the normal, to the interface. But we're actually going to do the analysis assuming that that theta is so close to zero, so small, that it's really coming in perpendicular to the interface. But we draw it this way so that the picture doesn't get too confused. Okay, so even though we draw the incident ray coming in at an angle theta to the interface, we're actually assuming theta is zero. Now what happens right here at this point where the ray intercepts the left interface? It's that point there labeled little a. Well, two things happen. Part of that incident light wave, and therefore the ray, is reflected back into material 1, and part of it is refracted into material 2. So here's the reflected ray coming back into material 1, and they label that reflected ray 1. And of course it would be reflected out at the same angle theta of the incident ray. And then here's the refracted ray that goes into material 2. Let's follow that for a bit. Well, once it's refracted into material 2, it travels in a straight line at a speed that's whatever the speed of light is for material 2 until it gets to the right interface, right at this point, which is labeled B, little b in the picture. What happens there? Well, two things. Some is reflected from that interface, and some is refracted into material 3. Here's the refracted ray going into material 3. We're not interested in it in this particular situation. Here's the reflected ray going back into material 2 and traveling in a straight line until it hits this left interface again at that point, which is the point labeled little c. Now what happens there? Well, part of the ray is reflected back into material 2. That's not the part we're interested in, it turns out. And part is refracted back into material 1. And that's this ray right here. And that ray is labeled R2. And here's what we're interested in. If we, as an observer, are located here, that represents your eye, then you will see these rays coming at you. And when those rays combine, what will be the phase difference between them? How can you get a phase difference between those two rays, and what will that phase difference be? Because knowing what that phase difference is, you can determine whether you will have fully constructive interference between the two rays, or the two waves, fully destructive, or intermediate. And we'll take the first two cases to focus on. Fully constructive means you'll see bright light. Fully destructive means darkness. What will our observer here observe? And why will there be a phase difference, potentially, between the two waves represented by R1 and R2? Well, we know one of the ways will have a phase difference between the two rays. The ray R2 travels a greater distance to get to our observer than the ray R1. Yes? Because the ray R2 has to make a diversion through layer 2 over to the right and then back again. And that's an extra distance of 2L. Remember, we're assuming normal incidence. 2L. And a path length difference results in a phase difference. So we need to be able to account for that path length difference and its effect on the phase. But there's another thing that's going to happen here that we haven't really talked about that gives rise to a phase difference between these rays, R1 and R2. And that's what I want to talk about now. Okay? It has to do with this key ID at the bottom of the screen. The phase difference between two waves can change if one or both are reflected. Can, doesn't mean must or will, but can. And I want to talk about how a reflection of a wave off of an interface can give rise to a phase change. I'm going to do that using a mechanical wave analogy, a wave on a string. And what we've got, and this will be analogous to our optical situation where the light is incident on an interface between two different materials with different indexes of refraction, and therefore the light waves in those materials travel at different speeds, v. Okay, now here comes a mechanical analog to that. Two different ropes connected together, tied together, at a point we'll call the interface. And in the first picture, the first rope is more massive. If you like, it's denser. It's got a greater mass per unit length mu, right, on the left. And the rope on the right is less dense. It's thinner. It's got a smaller mass per unit length mu. And we're going to set up a traveling wave or a wave pulse in the thicker rope traveling to the right. And here's the picture of it, approaching the interface. And it's traveling at some speed v1, we'll call it. Okay? On the thicker rope. When it gets to that interface between the thicker and the thinner rope, what happens? By experiment, by observation, you discover part of the wave pulse is transmitted into the lighter rope and travels at a faster speed, v2. And part of it, part of the wave pulse, is reflected back, traveling backwards at the speed v1. And the wave pulse that's reflected is still upright, like the original wave pulse. So there's no reflection of the wave pulse itself. When the reflection occurs at the interface, where on the right we have the lighter rope, where we have the wave pulse traveling faster. Now I want you to consider, and by the way, that's analogous in the optical situation to the case where we have an interface between two materials. The material on the left has index of refraction n1, the material on the right has index of refraction n2, and n2 is smaller than n1. Now I want to consider the second scenario. Again, we have an interface between two dissimilar ropes, but now the rope on the left is lighter than the rope on the right. See how the picture is drawn? And we're sending in initially a wave pulse in the left material, the lighter material, with a large speed, v1. What happens when the wave pulse gets to the interface? Well, some of it is transmitted into the second rope, which is the denser one, the thicker one, with the smaller v. And some of the pulse is reflected back into the thinner rope. But notice what happens to it. When the wave pulse reflects off of a thicker rope, the reflected pulse gets inverted. See that? That's a phase shift. It's a phase shift of pi radians, or a half a wavelength. You could think of it either way. Okay? Because the reflection occurred off of that thicker rope. And that's what caused the reflected pulse to be inverted. So that's analogous in the optical situation to an interface between two dissimilar materials with index of refraction N1 and N2. And now N2 is larger than N1. So in the optical situation, when will we get reflection? When will we get a phase shift in reflection off an interface? Okay? When will that happen? Well, this little table below is summarizing that. If the reflection occurs off of the material with the lower index, that's the top picture, no reflection phase shift, none. The pulse doesn't get inverted. But if we have reflection off of a material with a higher index of refraction, that's this picture, then we get an inversion, if you like. So we get a pi radian phase shift, or say it another way, 0.5 wavelengths. So we need to keep track of these situations here. And when we have light reflecting off of an interface, we need to keep track of, is it reflecting off of a material with a lower index of refraction? Or is it reflecting off of a material with a higher index of refraction? And if it's reflecting off a material with a higher index of refraction, we'll get an additional 0.5 wavelength or pi radian wavelength phase shift. All right, so now what we're going to do is we're going to take our picture of our thin film of thickness L, index of refraction N2, with our perpendicularly incident ray I, and our two rays that come off there, R1 and R2. And that's where our observer is going to be, and is going to combine those two rays in their eye, or in some kind of camera equipment, perhaps. But we want to know what kind of interference we're going to observe when those two waves interfere. And specifically, we want to know the condition for seeing a bright, fully constructive interference, or darkness, fully destructive interference. All right, now we're assuming in this picture that N2 is larger than N1 and N3, but the key thing is N2 is larger than N1. That means then, note very carefully, that the reflection at point A, which is for the ray R1, that picks up a reflection phase shift. So we're going to make an organizing table here. I think this is very helpful to help us figure out what kind of interference we're going to get where the observer is. And so one of the things we have to keep track of is if there's a reflection phase shift or not. And we have to do that for each of the two rays, R1 and R2. And since ray 1 reflects at point A off of material 2 with a larger index of refraction N2, we'll get a 0.5 wavelength reflection phase shift for ray R1. Now, ray R2 undergoes its reflection right there at point B, right? That's where the reflection for ray 2 happens, but that happens on the right interface, And that reflection occurs off of material 3 with index of refraction N3, which is smaller than N2. So for ray 2, we get no reflection phase shift. Okay, so when the rays, or the waves, R1 and R2 combine where the observer is, over here, they all automatically, already, inherently, have a phase shift difference between them of 0.5 lambda. And if there were no other physical effects involved, that 0.5 wavelength phase difference would result in fully destructive interference, darkness. But that's not all that happens here, because we also have a path length difference between rays R1 and R2, and that path length difference is 2L. Remember, we're assuming the rays go straight over and straight back, or the ray, R2, goes straight over and straight back. So it's 2L. So there is an additional phase difference between R1 and R2 because of the path length difference. Okay? And so we have to bring that into effect as well. All right, so let's think our way through what the condition will be for the two waves from the rays R1 and R2 when combined where the observer is to give us fully constructive interference in phase situation, brightness. Well, what I need is that path length difference, 2L, to result in an additional phase difference that's either 0.5 lambda, 1.5 lambda, 2.5, 3.5, 4.5, an odd half integer multiple of lambda, so that when that's combined with the 0.5 lambda that I already have from the reflection, I'll get an effective integer multiple of lambda, and then they'll be in phase. That makes sense? So, if what I want is the condition for fully constructive interference, at the location of the observer, I need 2L to be an odd integer divided by 2 times the wavelength. But what I need here, by the way, is the wavelength of the light in material 2, because that's where this extra distance of 2L happens, right? And that wavelength is the wavelength you'd have in vacuum, which I'll just denote lambda, divided by the index of refraction N2. Does that make sense? That's what I need to be true. And then the effect of that path length difference will be a phase difference that's an odd half integer multiple of lambda, and when I combine that effect with the effect of the reflection phase shift, I'll have fully constructive interference. Now, the way we denote that odd integer over 2 is we write this as m plus 1/2 times lambda over n2, where m just represents any non-negative integer. So m starts at 0 and steps up to 1, 2, 3, ... So for example, when m is 0, the right-hand side is 1/2 lambda over n2. 0.5, if you like. When m is 1, the right-hand side is 1.5 lambda over n2, etc. And so that's why you see this expression written right in here in the table. That's what must be true if we're going to see fully constructive interference where our observer is. We need the distance 2L and the wavelength and the index of refraction of material 2 to be related by that specific formula. then the observer will see fully constructive interference, and they will see brightness from where they are, looking down at the film. Okay? Let's also get this condition for fully destructive interference, where the observer is. Darkness. So now we want the net effect of the two waves at the observer to be out of phase. Well, we already got them out of phase from the reflection effect. So I want the path length difference effect to add an integer multiple of the wavelength. Okay? So that the net effect where the observer is an odd half integer multiple of wavelengths. So that the waves will then be out of phase exactly, and I'll have fully destructive interference. So what I want for my condition now is for 2L to be, well, just an integer, times the wavelength in material 2, which is the wavelength in vacuum, divided by N2. And the way we'll write that is we'll write that as just an integer m times lambda over N2, where m can be 0, 1, 2, 3, ... And that will be the condition for our observer. So we're at 2L to equal m lambda over N2, and you'll see that written right here. That's the condition, that's the relationship that has to be true between 2L, lambda, and N2 if our observer, where our observer is, looking down at that film, is to see darkness. Okay, so that kind of organizing table where you keep track of whether or not you get reflection phase shifts at the interfaces, and then also the effect of the path length difference and what it does for the phase difference, and then you just figure out, based on the reflection phase shifts you have and the path length difference phase shift, what relationship has to be true to get fully constructive interference and fully destructive interference. And then here's a special question to consider. What do we observe there, where our observer is, if the thickness of that film L is small compared to the wavelength of the light? Okay? That would be a very thin film. Usually when we talk about a thin film, we're talking about a thickness that might be of the order of millimeters to micrometers. A thin layer of something on top of something else, or surrounded by other things. But it could be very thin, like a nanometer, which is small compared to the wavelength of visible light. That wavelength ranges between about 400 and 700 nanometers. So what if it is a very thin film, so that L is small compared to the wavelength of the light? Well, if it's that thin, if the L is that small, we're in essence saying that the effect of the path length difference is negligible. The path length is in essence, the path length difference is in essence 0. And in a situation like that, then I'm just left with that 0.5 lambda reflection phase shift from R1 and no reflection phase shift for R2. So the observer, when the rays are combined, sees a phase difference of 0.5 lambda. That means they're out of phase. That means fully destructive interference. That means darkness. Note that really comes out of the out of phase equation at the very bottom if you just plug in the m equal to 0, which is allowed. And if the m is 0, that's like having the 2L equal to 0. You're ignoring the effect of the 2L, and it's going to be dark. So let me show you an actual photograph of thin film interference. This is a soap film. Very thin layer of soap with air on each side that has been illuminated from the front with what's called white light. And white light means just a mixture of all the visible wavelengths, from 400 nanometers up to 700 nanometers. And the soap film is held up vertically so that over time it starts to sink downward because of gravity. And so as you go from the top down to the bottom, the soap film gets progressively thicker. So it's not a constant thickness film in this particular case. It's getting thicker. And then they took a photograph of the reflected light that's reflected from the front of the soap film, as well as the reflected light reflected from the back of the soap film, and let those two waves interfere. Now, let me just point out a few things that we see. Here at the top, notice it's dark. Fully destructive interference for that whole region. That's because the film up there is so thin that 2L is small compared to the wavelength of the light, just like I was talking about, and you get fully destructive interference. Then you get this transition region, and then once you get right about down into here, you see bands of alternating colors with, if you can see very carefully, very thin dark bands in between. So there you're seeing, where at least the colors are, you're seeing fully constructive interference for the particular wavelength of the particular color that you see for the thickness of the soap film at that location. The bottom line, though, and it's pretty complicated stuff going on, it's also pretty, but the bottom line is those bands of colors are the evidence for the thin film interference. All right, so we'll be talking about this in the in-class video, but we're going to close this video with a class engagement exercise on Blackboard to practice with the thin film scenario. Here's the situation. The figure shows 4 situations in which light is incident perpendicularly from above, and it reflects from a thin film of thickness L. So that's the thin films we see here in the middle of these 4 situations. That's the key thin film in each situation, the one in the middle. Okay? And the indexes of refraction are given both for that middle layer of thickness L, as well as the surrounding layers on top and bottom. You can see the numbers there, the indexes of refraction for the 4 situations. Okay? So they show a light ray coming in. Apparently it's blue light in terms of its wavelength. They're interested in that part, and some of it will get reflected from that interface and go back. Some will go on through down to here, and it will get reflected and go back. And that will happen on all 4 situations. All right, here comes the first question. For which of these 4 situations do the reflections at the film interfaces, the top one and the bottom one, for each middle layer, those interfaces, there and there, for which situations do the reflections at those film interfaces cause a 0 phase difference for the 2 reflected rays? List the 4 situations for which that's true, for which the 2 reflected rays have 0 phase difference between them. Okay? Just from the reflections. And then B, for which of the 4 situations will the film be dark? Our observers up here above, looking down, in each case. Okay? For which situations will the film be dark if the path length difference 2L causes a phase difference of 0.5 wavelength? So our observers up there at the top, we've got these reflections we got to deal with. And now we're saying that the path length difference 2L causes a phase difference of a half a wavelength. For which of the 4 situations will the observer observe darkness, fully destructive interference? Okay? So those are the questions for that. And then we're going to have a class video where we practice with thin film interference. And that's all for this video.